This is probably for those of you who are physicists, engineers, and also mathematicians. This is where it's going to be probably the first introduction to something that you haven't necessarily seen before, or something that you've seen before that's going to be discussed in a very, very different way, a very general way, a mathematical way, and in a more abstract way, if you will. So a lot of it may seem a little odd. However, just by diving in a little bit, taking a look at some of the examples and letting them wash over you a little bit, you'll realize that it's not altogether different than what you've already been accustomed to. It's just looking at it from a different angle, from a more general angle. And again, that's what we do in mathematics. We take something and we try to generalize it as much as we can, to take that generalization, that process of abstraction, as far as we can. Okay, let's go ahead and get started. So this is an introduction to linear transformation, an introduction to linear maps. The first thing that we want to do is generalize this notion of a function that you've been dealing with for years now. So we want to generalize that notion, and that's what it is that we're going to be calling a map. So let's start with something that we do know. Let's take the function f of x equals x squared. Now let's talk about what this means and what it is you're actually doing here. It's saying take a number x from the real number system, do something to it, in this case square it, and then you're going to get back another number. So you're starting someplace, you have an input, this x value, you're doing something to it, that is your function, and then you're going to end up with something else. So in this case, if I take a 2, I end up with a 4. If I take a 3, I end up with a 9. If I take a 4, I end up with a 16. You know how to deal with this. You've been dealing with it for years now. Okay, let's represent this in a slightly different way. I'm going to draw a couple of pictures here. Okay, and I'm going to say this is my space of real numbers. You're used to thinking of real numbers as a real number line. That's fine. This is just another way of representing it as a set, as just a collection, a bag of numbers, if you will. So, and I call it R, because it's the real numbers. And I'm going to sort of duplicate that over here. Now I'm going to show you what it is that's actually going on. Let me pick a couple of numbers from the real numbers. Let's say 2, 4, and 6. Here's what this function is doing. You're taking a number from the reals, the set of real numbers. You're performing an operation on it, this so-called f, which is defined by this, okay? And you're getting back another number, 4. You're taking a 4 and you're coming over here, you're squaring it, you're getting a 16. You're taking a 6 and you're coming over here, you're getting a 36. So as it turns out, what you're doing is you're mapping 2 to 4, you're mapping 4 to 16, and you're mapping 6 to 36, and so on. In other words, to every number in the set of real numbers, you're associating another number in the set of real numbers. So you've taken something from the reals and you've ended up back in the reals. You can think of it as sort of ending up back in the same set, but we like to represent it this way. We like to think of them as two different sets. And we actually denote this like this. We say f is a mapping from the real numbers to the real numbers defined by f of x equals x squared. So this new symbolism is the symbolism that we're going to be using. This sort of implies that. You know what's going on, but now we're sort of breaking it down to say what it is that we're really doing. We're taking one number, we're fiddling with it, and we're spitting out another number, something from... So we actually treat these two spaces as separate. In fact, we call this the departure space. Not everyone refers to it like this, but I think it's the best way to refer to it. And this is the arrival space. In other words, you're taking a number from the departure space, you're leaving that space, you're doing something to it, performing, operating on it, whatever it is you want to call it, performing a function, and then you're arriving at some other number, some other place, the arrival space. Now in this case, you're starting with a number and you're ending with a number, but that doesn't mean you always have to do that. As it turns out, in a minute you'll see we can start with a number and end with a vector. We can start with a vector and end with a number, or we can get even more bizarre. We can start with one mathematical structure and end up with another mathematical structure. That's why this representation is the most general. So again, f is a function, is a mapping from R to R. What this means is that I pick a number from the real numbers, I do something to it, and I end up in the real numbers. That's what this symbol represents. And defined by, I actually give the definition of what the function is, what it is that I'm doing, what operation I'm performing. In this case, I'm actually squaring a number. Let's do another example. Let's say I have the function f of xy. Now I have two variables, is equal to x squared plus y squared. Let's just do a simple example. If I take the point 1, 2, okay, it's x squared plus y squared, so 1 squared plus 2 squared is equal to 1 plus 4, that's equal to 5. Now you've probably never even thought about this before, but take a look at what's going on. Now I'm taking two numbers from R, and the way this is represented, notice this is actually a vector representation. When I have two numbers like this, a point in 2 space, which is what this is, the point 1, 2, is also a vector in 2 space. So we represent that, of course, with R2. So when I symbolize this, according to how we did it here, here is what I'm writing. The function is a mapping from R2 to R, defined by f of xy equals x squared plus y squared. I could also write this in vector form, the f of xy. The vector xy equals x squared plus y squared. And again, this coordinate xy is the same as a 2 vector. So what this symbolism means is that my departure space, if you will, is now R2. It's the space of 2 vectors. My arrival space is R, the set of real numbers. I've taken a vector. I've done something to the individual components of that vector, and I spit out a number. So these are two different spaces. Even though I'm picking numbers, all the numbers are from the real number line, we actually consider this thing that we take, this vector that we take, as a single unit. So I took a 2 vector, I did something to the components of that 2 vector, and I spit out a number. That's what this symbolism means. That's why this is a very powerful symbolism, and it generalizes. This is a mapping from R2 to R. That means to the space of 2 vectors, I'm associating a number. To the space of to every element in the space of 2 vectors, I'm associating a number. I'm mapping a vector to a number. I'm mapping a 2 vector to a number. That's what's going on here.